Have you ever just stopped and wondered how the ridiculously complex devices we rely on every single day just work? I mean, we're talking about gadgets with billions of components packed into a tiny space. A single tiny mistake could be catastrophic. Well, it turns out there's this hidden war being fought on a virtual battlefield long before a single chip is ever actually manufactured. So today, let's dive right into the fascinating world of chip verification.
Okay, so meet the villain of our story, the bug. And this isn't just some minor annoyance. It's a potential multi-million-dollar liability. Finding a bug after a chip has been sent off for manufacturing, that's what they call tape-out, is an absolute disaster. You might remember the infamous Intel Pentium bug back in the 90s. That cost the company almost $500 million. So yeah, the goal here is to be ruthless, to basically torture the design in every way imaginable, to find every single flaw before it escapes into the real world.
And that really brings us to the core challenge, doesn't it? The point of verification isn't just about finding some bugs. It's about trying to prove that a design is perfect. But with the insane complexity we have today, how can you possibly test every single scenario? How do you guarantee a design will work flawlessly under conditions you haven't even dreamed of yet?
To really get the solution, we first have to appreciate the sheer scale of the problem. And this wasn't something that just popped up overnight. It was, kind of ironically, a crisis that was born from incredible success. You see, as Moore's law kept charging forward, the complexity of these chips just went through the roof. And all of a sudden, the old tools and methods that worked just fine for simpler designs were completely, totally overwhelmed. You could literally spend more time and money trying to verify a chip than you did actually designing it. Something had to change, and fast.
So what was this old way of doing things? Well, it was very methodical, very deliberate, and, as it turned out, dangerously limited.
It was a method called directed testing. It's exactly what it sounds like. An engineer would sit down, look at the design specification, make a list of all the features, and then one by one write a very specific test for each one. Like, okay, now I'm going to test the add two numbers feature, check. Now I'm going to test the write to the bus feature, check. It was this incredibly painstaking manual process. And you know, this approach looks great on paper. Managers love it because they see these nice, clean charts moving up and to the right. Progress. But here's the huge, glaring flaw. A directed test only finds the bugs you expect to be there. It's like walking down a well-lit, predictable path. The really dangerous bugs, the nasty ones, they're always lurking in the shadows, in those weird, unexpected interactions between features that nobody ever thought to write a script for.
This right here shows the difference perfectly. Directed testing, over on the left, it's like following one single road on a map. You'll definitely confirm that the road is there, but you'll miss absolutely everything else. The new way, constrained random testing, it's like sending out an army of explorers to map the entire territory all at once, finding all the hidden caves and those totally unexpected bugs. So this new way of thinking, it wasn't just a small tweak, it was a complete paradigm shift. It was time to stop hunting for bugs one at a time and start flushing them all out at once. Instead of having engineers manually write every single test, the big idea was to automate the whole thing. The goal was to generate just massive, overwhelming amounts of stimulus automatically, this intelligent chaos army, to just bombard the design with a huge variety of inputs, transactions, and scenarios, all happening at the same time. Now, the really clever part here is that word constraint. See, this isn't just pure random noise. That would be totally useless. Instead, the engineers write a set of rules, or constraints. Things like, the memory address has to be a valid 32-bit value, or the data packet length can't be more than 32 bytes. The simulator then generates random values that obey those rules, making sure that all that chaos is actually powerful and, realistic. And the results are, well, they're dramatic. You can see it right here. A single directed test might cover one specific feature pretty well, hitting maybe 25% of the possibilities. But a single random test, just by its nature, explores a much, much wider space. So when you run thousands of these tests, all with different random starting points, you get this massive coverage. We're talking 85% or more, and you find way more bugs way faster. But all this chaos, it creates a brand new problem. If you've just unleashed this army to attack everything at random, you need some way to track its progress. You have to know what's actually been tested. And this is such a critical question, right? If you don't have a way to measure what you've done, you're basically just running simulations in the dark.
You have no clue if you're actually getting closer to your verification goals or if you're just spinning your wheels, testing the same things over and over again. The answer to that problem is something called functional coverage. What you do is you add special monitoring code right into your test environment that acts like a checklist. It just watches the simulation run and ticks off boxes. Hey, have we seen a packet of size X? Check. Have we seen a memory read immediately followed by a write? Check. Have we tested this very specific error condition? Check. It's the perfect analogy. Think of it like a reconnaissance map that gets filled in by your chaos army. The coverage data shows you exactly which parts of the design space you've already explored, but even more importantly, it shows you the holes, all the features and scenarios that your random tests haven't managed to hit yet. And this creates this incredibly powerful feedback loop. It's a cycle. You run your random tests, you look at the coverage reports, and you see a hole. Then you go in and you add a new constraint to specifically guide that chaos army toward that unexplored territory. And you just repeat this process over and over, systematically closing all the gaps. This whole iterative process is really the heart of modern, coverage-driven verification. Okay, so this entire war against bugs, this chaos army, this feedback loop, it all has to happen somewhere, right? Well, it's all waged inside this incredibly sophisticated virtual simulation of the real world. You know, to test a chip, you can't just test it in a vacuum. You have to build an entire world for it to live in. You have to simulate everything it's ever going to connect to. USB ports, memory, networks, you name it. And you need a really powerful language to describe that perfect, and sometimes not so perfect world. And that virtual world, that's called the test bench. It's this massive piece of software, usually written in specialized languages like SystemVerilog, that basically wraps around the chip design. It pretends to be every other component in the system. It's what generates all the stimulus, it captures the chip's output, and it automatically checks if the response was what it was supposed to be. But it's not just one giant blob of code. A really good modern test bench is built in layers. At the very top, you have these abstract goals, like download a file. Then, as you move down through the layers, that simple idea gets broken down into smaller and smaller pieces, into transactions, then into commands, until at the very bottom, you're just flipping individual bits on the virtual wires connected to the chip. This layered approach is how you manage all that complexity. And this structure is just brilliant because it takes what seems like an impossibly complex problem and breaks it down into these manageable chunks. Each layer has exactly one job to do. This makes the whole test bench way easier to build, easier to debug, and maybe most importantly, you can reuse parts of it across many different projects. And ultimately, that's what this is all about. Chip verification has evolved so much, from what was basically a simple bug hunt into this highly sophisticated, automated discipline. It's a systematic process that gives engineers a map and a compass so they can successfully navigate the absolutely staggering complexity of modern hardware. So the next time your phone or your computer or your car just performs flawlessly and doesn't crash, just take a second. Think about the invisible war that it already won before it even existed. Think about the virtual world it lived in and the intelligent chaos army it had to survive, all to make sure that for you, it would just work.